Okay folks, so I noticed comparing that against I compared this against my test project. I noticed two things. That in my test project I do not have this reset pin and I don't have any I2C connections. So these 4 and this 5 I want to remove. And what I want to do is remove them here. So this is the reset. I don't need this. I'll remove it. Oh, sorry. I'll remove this. I don't need this. There's no reset connection anyways. And memory stays, HPS IO stay. And what else? I need to remove the I2C parameter connection. So I2C, sorry, peripheral connection. Peripheral connection is here. I2C pin 0 unused. And wait for a little bit here. Unused, no I2C, not 0, not 1, no I2C. Okay, now I save this. Save successful. Generate HDL again. Let's see how quickly it goes now. Let's see how quick it is now. I may have to come back. It looks like it is going through this whole process once more. So let's come back to this when it's done. Okay, now that it's complete, I'm going to close this. It generated. Now I'll take the instantiation template again, close, and come back to our code again, and I will paste over our component and the pin mapping. So, or port mapping I should say. Control X, so I'll take the port mapping. This is our port mapping right here. The old one is replaced, and take the new component and put it up here as well. Component right here. Okay, so now I don't have I2C, I still have reset. I don't know where it's coming from. Very interesting. I still have reset. Okay, I will keep it open. And let's see where this fits. Now another thing I did is I've already copied this all these connection points that we have to make connection to in our architecture, and I will bring it. I'm bringing it here. I'll copy paste here, and you'll see exactly these are. So these are basically copied from the GHRD again. So when I go to my GHRD and look for my, this is created in Verilog. So let me show you what this is. Hold on. Okay, so this is my GHRD, and in the GHRD These are all the connection points. So essentially for VHDL, I copy them over and rearrange them for the, or basically you can say adapt this portion for the VHDL code. The adaptation essentially gives me this. So for those of you who want this to be typed out, FYI, it will take longer. It's better to just pull it into an Excel file and edit, copy paste, or find and replace, and add these different standard logic and logic vector portions in each, and that's all you need though. So now what we will do is we will separate out the ENET, DDR3. There's I2C in there. Now I see it. I don't know, I didn't saw it before. So I think I'm not using the I2C. I just didn't use them. It's there, but I never used. In any case, if it's not used, not used. If it does complain, I will add it in. For now, let's keep it in there. Okay. Alright, so all those connections must be connected here. This reset one, I cannot figure out how did I remove this? There's no other reset left. H2F reset is disabled. It's removed. There's no connection left. Yet it wants to hang on. Okay, reset and okay, let's start with the easy portion of this. Yes, clock 50 goes to the clock. And basically you'll do it like this. Our export, this one we will create another signal. And this will be called HPS counter. HPS counter, let's say HPS counter in. This is a input to FPGA. And let's see. Reset, we will leave it for now. For the reset, I'll just create a reset N signal. Okay. So reset N is reset N. Not used, not utilized. It's just a unused piece that we will keep it in there. It's in there for some reason. I have missed how to disable this. but no worries, we can still continue. So EMAC, let me separate these a little bit so we can see the different pieces that we have to connect, because each one if it is divided in multiple bits, we have to define each one separate. Okay, this is right here. Okay, so let's take our CONV USB. This is a USB-N. This is our GPIO 9. Then, okay, ADDR. Now ADDR is going to be separately connected. Maybe not. ADDR, DDR3. It's connected to mem-A. ADDR. Okay, so you get the idea. Now, use the GHRD as your reference, or you can follow this, and it's just going to take a little bit of time to go through this. So BA is BA. Maybe I should make a script to make these connections. CKP. CKE. CKE is CKE. Memory is straightforward. CKE is here. Oh, wrong one. CKE is here. CSN. Wonder if I can divide this into two windows. DM. DM is DM. DQ. DQSN. DQSN. ODT. ODT is ODT. Okay, so basically you get the point. I will continue and come back to the video when I connect all of these pieces together, and then we will be ready to execute the compiler. Okay, so now I copy all the components I've taken from the GHRD project, It's not every single one of them, but the ones that apply to my project, and I connect them to the port component declaration. Essentially, this is where everything is going to link to from that outside connection. And we have one thing that I want to use here, that I want to take into our current code. I want to bring it down here. Let's say right now we have a pulse out, and our pulse output depends on the switch, that the 4-bit switch we have configured. Now what I want to do is take that in, which is a 4-bit in from the HPS, put it against the comparison here, or make a comparison to the switch bit. Well, not the switch bit. Now this is the in counter from the HPS. What we are going to do, similar to what we did for the switch, we will also have a HPS counter, and this is not a in, this is just a counter, and this is the HPS count. Okay, so our HPS counter, when it's equal to the HPS in counter, we're going to put out a HPS pulse out. And the switch counter will be, as we are setting that to 0, we're going to reset our HPS counter to 0. Otherwise, we keep incrementing, make sure our 0 state is verified. And now, using the same 762 Hertz clock, we are going to evaluate. We could evaluate at a faster rate. Maybe we could evaluate, because now it doesn't depend on the 762 Hertz anymore. It now depends on the HPS. HPS is running on a 50 megahertz clock, so we will check it against that. And let's say, yeah, we need the HPS pulse output. I believe I already made the signal for this. HPS, yeah, right here. I need to do it here. I don't know why it likes to do that. Alright, HPS pulse out, and what else we need here? We need another LED process after this. I'll call it LED 2, and we can say LED pin 2. We will change the state of the LED pin 2, and we will change the state of the motor GIO pin 2. So we'll keep the original one in place just to test the current state of the FPGA. Alright, now let's say we need LED pin 2 and we need motor pin 2. second pin for the LED, and a second pin for the motor. So I'll just say these two. Okay, now here we are. LED pin 2 and motor GPIO pin 2. This is good. This is good. Let's see if there's any error. It will scream out to us. I've created some gaps here. Let's see how, if it's happy, if it's happy. If it's happy, I'm okay. If it's not, then I have to consider making minor changes. Control S, save, and do a synthesis. Make sure that overall the program is okay. Then we go into compilation. Oh, before we go into compilation, we do have to connect those new pins. So okay, let's complete it. Let's allow it to complete the synthesis, and there is some issue. Let's see, but not declared. RX enable, not enable. This is the enable, RX enable. Not UART. Let me see again. This is a ENET RX control, and then ENET 6. Sorry, ENET TXEN control. So there's a RX and there is a TX. I think I made a copy paste mistake here. Yeah, that's what I did. Yeah, it's not TX. Okay, what else? 2 errors, 1 warning. Let's try again. Oh yes, we didn't took that step yet. Alright, so now that we have the SOC project defined, the FPGA project, the VHDL, needs to know our component file as well. So we will do a add. It opens up in here for some reason, and we will add our either the Q. We can take the QSys or we can take the QIP file. We can do that. So I'll take the QSys and make sure this is the top. QSys is not the master. Our FPGA, the VHDL file is the master. So it will remain at the top. And what we will do now is we will map the remaining, or the new two additional pins that we added. They are not okay. Its synthesis didn't complete. So let's do it again once more, and let's see. It's going to scream further. So there is another step I know we haven't done yet. I want the pins to be available. Then I'll execute. There's a step to execute something called TCL scripts. Basically, the QSys project that we create has its own internal connections. The TCL scripts allow the project to make those connections to the original project or the master project. So let's allow it to complete first. Let's see if it does that. Maybe I have to compile it twice to complete those connections. Let's see where it goes. Okay, so it completed. This was just this, we use this option to run, let me see if it gives us, yeah, the analysis and synthesis option. Now it should realize the additional pins, and yeah, there they are. Okay, and out of these additional pins, the ones that are intended for the QSys project, we will leave them alone, but we will only modify our LED and motor pins. So I'll get to that why. Just hold on for a moment here. Let's modify this this code or assign the pins to this project, and then I'll explain what's going on here. Okay. Alright, that's where they are. Where's my pin map? Pin map is here. LED 2. Well, motor pin 2. Let's do the motor pin 2 first. Motor pin 1 is AH3, pin 10. I'll take this pin 8, AH14. And now what I'll do is find my LED. I'm already using AE26, which is number 5. Let's use W15. For our HPS. So whenever the frequency will change, you'll see the change in the light light output. Okay, now coming back to why we are leaving these others. So what happens is when we execute our project, TCL scripts and the entire project, we have to execute it twice. FYI, maybe the first time the TCL scripts won't connect all the way, so maybe we have to do it again. But essentially what happens when we execute the compilation goes through these pins, automatically checks the name. So the naming is very important as well. I'm not sure exactly, it has to be exactly the same or not, but I know when you make that component connection, it knows exactly which one of these are supposed to be connected to which pin on the Cyclone 5. So as it executes its compiler, the compiler figure out these connections and it automatically assigns. There's a another column that will show up here once we execute it, and in that column you'll see those assignments aligned automatically, and then we can do a cross check to make sure that those connections are made. So we'll do that after the compilation. So basically what I'm saying is that once the compilation completes successfully, it assign all these HPS connections to the right pin connections or pin locations in the Cyclone 5. So we don't have to worry about them right now. We will check them later once the compiler is done. We will check them. Okay, so let's close this for now. And what I'll do is I'll try to run this TCL script. Let's see if this, I'm not sure exactly when this is supposed to be done, but I know it is supposed to be done. And in our case, for now, we have two different SOC system files. Our project should not contain two, but it does. In any case, what we want to do is basically run the two scripts. The parameters, you see this S0MP0 parameters, and then S0MP0 pin assignments. That's it. These two have to be run, and they are also present under the synthesis. I think I didn't disable the synthesis option. Maybe that's why it showed up. I have. I'm pretty sure I did. Okay. In any case, we we want to make sure that these connections are made. So let's run these scripts. The parameter runs flawlessly every time, no issue there. And as soon as I run it, you'll see this 0.06076. That's the time it took to complete. So no issues here. So basically, the output of the TCL scripts will be displayed here. Let's see if we get an error in this one. Sometimes it does. So let's see. It shows up now. Yes or no? Yes or no? Feels like it will. It was successful. Okay, so this is the submodules are okay, and the SOC system file, we will run for that as well. Same thing. And assignments. Pin map is not done yet, so I don't think it will be successful. We can try to do this. I could try this, but I'm sure it will complain. Yes, it does. Because pin mapping is not done, the compiler hasn't assigned those pins yet. So this will be a problem. So just the parameter and assignments, that's it. We're going to run, close, and we are going to start the compiler. And now it's going to compile. And I'm going to stop the video here and come back when I see a result from the output from the compiler. Okay, this was quick. So now it's done 100%. I do not see any error in the processing side. This is our TCL output, if you remember. The pin map TCL script created this error. But in the processing, compilation is telling me 0 errors, and I think this is complete. Now we will go back to our pins and let's observe what the pin map looks like. Okay, let's expand this. Okay, so as you see, after we compile, the compilation must be successful in order for this to happen. So if the compilation didn't succeed, you will not see this result. So if you remember, we didn't assign any pin, but you see there's another column the compiler has created. So the compiler created this filter location column, and even the IO standard and current strength and all those details, they're filled in. Each of those we can go back and we can check. For example, let's see if we can check. Which one do we want to check? Let's see. SD C13. If there's a C13 defined, it should be SD data 0, SD data 0 C13, SD data 1 B6, and so on. You can see SD data 3 is B9. And we can do a little spot check here as well. DDR3, let's say pin 0. Pin 0, where are you? Yeah, pin 0, J25. J25. DDR3 is J25. Let's say we want to look at pin, sorry, DDR-DQ25, and that will be R25. So R25 right there. So yeah, this is what it does. The platform designer output or the connections from the platform designer component within your FPGA code, when it's linked to the port mappings into your top entity up here, the compiler recognizes these connections, and it automatically assigns the correct pin associations. Obviously, remember, for this to be correct, you want to be sure that your project is configured for the correct device. So if you are using D10-nano, using this instruction, yeah, make sure that it is this. And the best way to check this for your particular card is to make sure that the model number, device number written on your Cyclone chip matches matches the device configuration of your project. Otherwise, obviously, the compiler doesn't know your physical hardware. Whatever you configure in your project will be the one it will take and configure your entire project for. So yeah, be careful before you run this compiler. Make sure the device is correctly defined, and each of these connections are correctly related. Obviously, if there's a misconnection, let's say for example, if I'm not assigning the data to the data output pin, and maybe the command pin is assigned, then it will obviously throw an error. It'll say, hey, that's not the right dimension for this component. So alright, so this is the compilation. We will go to the next step, and the next step will be to convert into RBF file, and from that we will take that RBF to the SD card. Okay, let's stop it right here, and then I'll continue in the next video. I came across this interesting message when I try to open Quartus. It says that my Prime software expires in 10 days, and I did look up. This is the first time I've seen this message, so I'm really puzzled what is going on. I looked up on the Google and found out that other people have the same situation while running the Quartus Lite edition, and their version kept on running after the expiration date. So maybe it will keep on working. If it doesn't, I will uninstall and reinstall the newer version, or try to change the version. We're not doing anything advanced at this time, just basic FPGA and SoC combination. So I don't think it will affect our project at this stage. So I'll do continue or cancel, and this should open. Okay, so at this step what we want to do is we want to convert our SOF file into a binary RBF file. The RBF file, why we're doing that is because I want to use the FAT partition to basically what I want to do is I want to utilize the HPS portion to program the FPGA, and HPS for this SD card image, there is a separate FAT partition created that the HPS reads at its initialization, and it then picks up this RBF file and programs the FPGA. It's much more cleaner. We don't have to worry about flashing our EPCS every time there's a new program. We just change that file, and the HPS takes care of the programming side. So let's convert the file. Let me open the project first. So our project was this guy, and let's see. Okay, now it's open. Convert programming files. So maybe I went a bit too quick. Let's do it slowly. Under File, click this Convert Programming Files, and you will see this tool. And in this tool, you can convert the POF file into the RBF file. So what we will do, we will select our RBF option, and in this second row, this is a important selection. You can leave it to 1-bit passive serial. There is a test I need to do with a 32-bit parallel combination that works under the same mselect configuration, the switch configuration, under 32x32 configuration, and for some reason it is not working for my programs. So by default I'm choosing to use 1-bit. Basically it's the programming method, or you can think of it as a buffer that saves the program at one time and then programs the FPGA. So in our case it's going to be 1-bit at a time. It can do a 16-bit buffer or 32-bit buffer. So in that sense it'll make sense. So that's basically how it does the programming. So what we will do right now is take the output file. I thought it was an output. Apologize for the noises. Synthesis submodules. Why I'm picking up RBF file? I don't want to pick up RBF. I want to pick up my SOF file. There you go. There's my SOF file. It's pretty much straightforward, so all I have to do is click generate, and this will generate the RBF file. And there you go, the file is created successfully. Okay, we'll come back to this, and we'll come back to this. Okay, let's move to the next step. Okay folks, so we have generated the RBF file. Let's see where it's saved. I'm going to check my output path. It should be in the main directory, in the project main directory, so it should be right here. This is the RBF file. Okay, so now that we have the RBF file, now we need to put that in this put this file in the right place where the HPS can pick it up and program the FPGA. So let's look at our SD card. I'm going to plug in my plug in my D10-nano, and let's see. So I powered up the D10-nano, and I moved my USB connection to the UART so I can look at the console. And let's say we have our PuTTY. I'm going to open PuTTY. This is to figure out the assigned IP address. As you can see, I have the Ethernet also connected. Our IP address is 10. And what I want to do is, I like to do this over my terminal connection and UART, because I don't want to use UART because I cannot copy over any commands if I need to mount the the drive. So PCMan FN is our file manager, and what we want to do is go to device and load up the, I believe it's the first one, MMC BLK0, or it's this one. It's one or the other. So one of these two devices are our how can we mount it? If we can mount it here, there should be a way to mount it here. Let me look at the applications, internet accessories, system tools, task manager. That's just the CPU. Let me see if I have saved. Oh, I haven't. Okay. So what I want to do is mount my device, and I believe well, let me check my options for mounting, if there's any simple example in the mount. Mount device, there it is. This is what I want. So I need just this. Oh, I do need the folder before I do this. So what I mean by that is the place I want to mount has to be a folder, and essentially in previous device, or maybe for this one, I created a mount point or mount folder. Okay, so I'll choose this mount, and let's do a ls device, and the ls device, let's mount this and let's see what's inside. Already mounted or busy, so okay, that's not the one. Okay, what else do we, oh, maybe it's in media already. Hold on, maybe it is, right? Let me check. Alright, it's not there. Core boot, no, okay. Let me try the other one. BLK0P1. Ah, there it is. Okay, so you see now it's the MMC BLK0P1 device is where our FAT of FAT partition is located. And let me think here. What I want to do is pass this file into here. I want to copy it over SSH there's a command called SSC to copy over the file over the network. Let me see. This is the mount. I do want to use the PCman. Let's utilize our file manager. So I'll go to the home menu, home, root folder, mount point. This is our mount location. You can see that this boot SCR, SOC system RBF. Let's do it in the list format. List view, yeah, this is much better. SOC system RBF. So what I want to do is create a new folder called backup, and as soon as it creates the folder, yeah, okay, I'll copy this in there. Okay, so that RBF is saved. Now I want to come back to our laptop, and here I want to say, let's go to that location where our FPGA project is situated, and we will take the location of that. Or I can say, instead just SCP, and take the location here. I don't need to know the name, it's just one file. So I'm just going to say, oh, whatever RBF file is there. I want to copy this over. .40.10. Actually, it's going to be in mount. And here it is. Okay, so it tells me that it copied. And we can go back to our PCman FM, and there it is. There's our output file. All we need to do is get rid of this guy, and it is going to be SOC system RBF. Okay, now this is our programmed FPGA file, and you'll see when I reboot what yeah, we can follow our console output, and we can see exactly the status. We do need to see that because there is one other step I want to practically show you. What will happen. So remember, we converted the SOF file into RBF file, and then we moved that RBF file into this D10-nano SD card image, and we also changed its name to match the one that was there, that was loading by default, basically replacing that file. And now when we reboot, it should reboot. Putty is not rebooting. I'm going to force reboot it. Okay, so this is the point I want to demonstrate here. So from the console connection, what you will see is that, hey, I'm rebooting, and it will say, hey, there's something weird going on. Oh no, not here, sorry. There's something weird going on, and it's trying to read the RBF file. This is our SOC system RBF file. And it says, hey, I cannot load. And then it just basically halts. Kernel does not load. So if you remember, we in Quartus, when we convert, so this is the convert programming file. I still have it open. We use this first option, 1-bit passive serial, and if you remember, I was referring to X32 configuration in the M cell. Let's see. Yeah. So 32-bit configuration is basically 01010, and right now our board is configured for 01010. Oh, I'm sorry, my video is blocking the view here again. There you go. So you can see this is 32-bit configuration. Let me see if there's a better view of this. Yeah, so this is our current switch configuration on the D10-nano that you see in the picture. 01010. Now, and my video is frozen. That is nice. That is just nice. Okay. Okay, it's going again. Okay, so what I was basically trying to show you here is that our current configuration is 01010, and basically this is for the X32 passive parallel configuration. Now with this current compilation, the configuration that is compiled for by default is X16. It does not allow me to compile in X32. I don't understand why, and I don't want to get into that right now. I do know that in order to run my program in X16, even though I use the very first option, it still wants to load as X16. So there's some other homework I need to do to figure out how to make it run under X32 pin configuration. But for now, again, like other situations that we went through, I'm stepping over that. I don't want to focus on that. I want to focus on finishing my project. So what we need to do is basically change this to all zeros, which means that if we can find the picture of that, or better yet, this configuration, so all on positions basically. So if I change this to on, it will be ready for X16 compression. FFP, sorry, I apologize, FFP X16 configuration. So now when I reboot, let's go back to our console output, and this should boot. Something isn't right. I guess I have to see what is going on.